Okay, welcome to a little discussion on radical expressions and radical functions. You can see we're going to analyze the graphs, evaluate different expressions, and also deal with what the inverses look like. So let's get started. We know we worked with radicals in the past. They've been square roots for the most part. So if we think about what we've done recently, we'd have the square root of 25, the square root of 100, and maybe even one that's not a perfect square like the square root of 35. And we were able to analyze those. Well, now you're going to see when we expand our knowledge of radicals, they don't always have to be square roots. In our square roots, we did not see anything sitting here. It was understood to be a square root. It was the most frequently used at this point. But now you can see we're going to add 3s, 5s, 4s, other numbers there, and those numbers are going to be called the index. That index describes what type of root you actually have, and again, the number underneath will be the radicand. Okay? So in this situation, you ought to be thinking, when we're looking at the cube root of radical 25, what is that one number that multiplies by itself 3 times to give you the number 25? Some of them are nice, just like the square roots were, came out to be perfect square numbers. Some of them are not so nice, like the square root of 35 was not so nice, did not come out to be a nice whole number. So in this case, the cube root of 25, again, not so nice number. But remember, we now have also our cube roots that we got to think about. Before, the square root numbers, or the perfect square numbers, were key to help us do square roots. Well, now the cubed numbers will be key in helping us do cube roots. So let's look under the simplified ones here. If I say, what is that one number that multiplies by itself 3 times to give me 27, your answer would be 3. If I said, what is that one number that multiplies by itself 3 times to give me a negative 27, you should be saying negative 3. Because 3 negatives gives an odd amount of negatives, and that would lead us to a final answer that was also negative. What is that one number that multiplies by itself 5 times, a 5th root in this case, to gives us the number 32, and that should be 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And again, notice, when these are perfect cubes, perfect 5th root numbers, they come out as whole numbers. There's nothing left underneath. Now, let's do one. The 4th root of 16. We know 2 times 2 is 4, times 2 is 8, times 2 would give me the 16. Again, a perfect rooted number. Right? There will be times when it won't be a perfect rooted, and you will have to break it down, very similar to how you had to break it down with square roots. But right now, we're keeping everything nice and clean. All right, next one. What is the cube root of negative 125? What is that one number that multiplies by itself 3 times to give you a negative 125? And the answer is negative 5. Okay, usually it's one or the other, not both, when we're talking about positive and negative square roots. Now, let's go back to that 4th root. Could I have taken a negative 2 and multiplied it by itself 4 times and also gotten that 16? Because I believe that's one we missed in our discussion, and that should have a plus or minus on in most situations. But you're going to see in the book, and it'll even say that we're considering this notation without a plus minus to be what is the positive 4th root of 16. So if they wanted you to do the plus minus, they probably would have had something like that in the original. That's all we're saying. Okay. So moving on. Now evaluate each expression. So now we got a little more going on. Let's see what would happen. So I see some multiplication right here. I got a negative 6 times this radical, and then after the radical I've got some subtraction. So let's do the radical first. So what is the cubed root of negative 8? What is that one number that multiplies by itself 3 times to give me a -8. And most of you would say -2. Well, then that becomes that whole number of -2 with that -6 out front, and then we still have subtract 2. And as you know, multiplication comes next. So -6 times -2 is 12. 12 subtract 2 would give us an answer of 10. Final answer there is 10. Next one, we got a cube root of 216. The numbers are starting to get a little bigger, but again, still work with it. You can't do it in your head. You always have your calculator. But we definitely have this parentheses that has to be evaluated first. Then it looks like our power would be next, and that multiplication by 4 would be last but not least. So the cube root of 216, you're thinking, I don't know, my times table is that bad. We knew the the cube root of 125 over here was a 5. So if we just go one higher, and even if you don't know, you know 6 times 6 is 36, so you're just doing 36 times 6. 6 times 6 is 36, carry the 3, oops, we found it right away. So we know that the cube root of 216 is 6. If we squared it, we would get a 36. And then we're going to have 36 times 4. 6 times 4 is 24, carry the 2, and we're going to get a 144 for our final answer on that. Okay? So all different looks at different kinds of radicals, whether it's square roots, cube roots, fifth roots, sixth roots, or whatever. So now let's look and see what happens when we take these radicals and actually graph them. Now, we have not even done that many square roots, so let's start there. If our parent graph is f of x equals the square root of x, we want to know what it looks like and what its domain and range is before we even start translating it or moving it around. So, as you know, when we put the square root of a -2 up there, we get something called an imaginary number, which means if we're graphing in a real number system, which is what our graph represents, we'd have an error. Same thing, the square root of -1 is an I value, which is imaginary, we'd get an error. What's the square root of 0? Well, we know it's 0. And then the square root of 1 is 1. Square root of 2 is the square root of 2, 1.4-ish number. We could do a few more if we wanted. Square root of 3 would be a square root of 3 if we did the number 4. Square root of 4 is the whole number 2. So we had a few numbers that we can now graph. So let's see what happens here. If we put a 0 in, we got 0. If we put a 1 in, we got a 1. We put a 2 in, we got the square root of 2, which is 1.41, so a little less than. Should make the dot about as big, though. 3, 1.7-ish, I believe. It's a little higher. Still just as much room. 4 is a 2, exactly. And we're starting to see this curve, as we say. Whoa. Okay. We know, for example, when we do the square root of 9, which is out here, we're going to be at 3. So 5, 6, 7, 8, 9, we're going to be right on 3, So we can see some of our choices, and it's going to continue to grow as we get going. Now, it's just a curve. There's nothing more to it. So, right now, what would we have to say about our domain? All possible x values. In this graph, the only x values we're seeing are x values, all reals, greater than or equal to 0. We're not seeing any negatives on this. The range, start looking at it. You're looking up and down the y-axis and seeing what you have graphed. And again, I believe we're seeing all reals such that that was x greater than 0. Now range is y values greater than or equal to 0. So we've got fractions, we've got whole numbers graph there up in this category. So make sure, again, we haven't done this in a while. For domain, your eyeballs are looking left to right. And for the range, your eyeballs are looking up and down. Okay? So now you have an idea of what would happen if we translated that. And we definitely are going to transform it because we've been transforming different styles of graphs all year. So if we have that situation, here is an example of what's going to happen. let's start again with our idea that this is my parent graph. So we had that as our starting point. And now, when you look at it here, you could have something happening out front. We're calling that the A value. And that A value would represent vertical stretch or compression. It's the same situation you had when we did quadratics like this, when we did absolute values like this. So we're not changing it, but we're just reminding you. So the vertical stretch or compression by the absolute value of A, for a factor of A. For A less than 0, though, the graph is a reflection across that x-axis. Okay? The B value, next, will be a horizontal stretch or compression by a factor of the absolute value of 1 over B for B less than 0. Otherwise, it's just the stretch in the positive range. The graph is a reflection across the y-axis. The x is part of the equation, and then we have the minus sign. So if you minus h in green, you can see the horizontal translation, h units to the right for h greater than 0, and the absolute value of h units to the left for when h is less than 0. Last but not least, the k value. Notice it's out here outside of the square root sign completely. It takes on a vertical translation of k, and it'll be k units up when k is greater than 0, and the absolute value of k units down for when k is less than 0. So just to show you an example, here I have one. So take a look. What's outside the square root sign, what's inside, what's underneath, what's been added, what has changed. So if you look and start comparisons, I think we have an A value on this one that we didn't have before. We have a H value on this one that we didn't have before. And we have that K value that's outside of the radical sign totally. So start thinking about what each of those mean. The 3 out front, make your choice. The 2 underneath, make your choice. And the 5 that's outside of the radical totally, make your choice there. And did you say that we will have a vertical stretch by a factor of 3, a horizontal translation 2 units to the right, and a vertical translation 5 units down. So again, you're not having to graph it, but you should be able to tell by looking specifically from the original parent graph, the parent graph, and comparing that to what we're expecting, what we've been studying. Here's the parent, and compare it to all the possible changes that could happen. And they're the same changes we've been using throughout the course, so we're not changing that on you now. Okay. From there, let's go to what happens when we graph a different style of root. Is it going to change our results any? So we have a cube root. Let's assume our parent graph is the cube root of x. And again, when we always graph, we want some positives, some negatives, and zeros. And because it's a cube root, I was trying to stay nice to our brains here and work only numbers that we could do in our heads. So be careful what you get and choose carefully. All right? So I have a negative 8. If I put negative 8 in for x, take the cube root of it, I'm going to get that negative 2 value. If I put a negative 1 in, what is that one number that multiplies by itself 3 times to give me the negative 1? And that would be a negative 1. What is the cube root of 0? Well, of course, that's 0. What's the cube root of 1? That's 1. What's the cube root of 8? And that would be a positive 2. So we could now graph that on our number line here, coordinate graph, and see what we get, and then we can answer domain and range a little easier. So a negative 8. We went down to negative 8 and down to negative 2. We would have been here. And then we went negative 1, negative 1. We went to 0, 0. We went to 1, 1. My pen stopped. Okay, we went to 1, 1. And then we went to 8, 2. We can see we're getting a little S shape. It's fairly elongated though. In our work for our cube root graph. So now, again, look left to right for your domain. What are the possible x values that we have graphed to include this cube root graph? All right, looks like we've got lots of positive numbers, lots of negative numbers. So I'm going to say all reals, not just whole, not just fractions. Then the range, up and down. Look at it. Some of you would like to say, you know, it only goes so high or so low, but right now we've only graphed a very small set of numbers. So I think in this case, again, we're going to have to say all reals. Up and down, we have fractions, we have whole numbers, we have decimals graph. And even if we get bigger numbers involved, I think we're still going to have that. All right. Last but not least, if we say, find the domain of this function, and my function is h of x equals the square root of negative 4x plus 7. Now, we know a square root can only be true if what's underneath is not negative. So that's your thinking on these. You would take whatever is underneath your square root and say it must be greater than or equal to 0. Because without that, we're going to get our negative number, we're going to get an imaginary solution, and that would not graph in the set of real numbers. So when we graph this, solve this, we get negative 4x is greater than or equal to a negative 7. We divide by a negative 4 on both sides. And remember, when we divide by a negative, we're going to have to switch that inequality. So x is less than or equal to a positive 7/4. So our domain, only thing that's going to work for this particular square root is going to be all x values that are less than or equal to 7/4. Those are the only numbers that will keep our radical positive or 0. All right, last thing. We've also done inverses in the past, so a quick reminder. To solve for an inverse equation, switch x and y, and then solve for y. So this equation says find the inverse of y equals x squared plus 1. Then graph the function and its inverse. So here is our function. We like to call it the original or the parent graph. And in order to get its inverse, as we said, we've done before, we'll flip-flop x and y, face value. So we would have x equals y squared plus 1. Now, that's not a very good look. Number one, because we have two different variables in it, and number two, for graphing, which is everything's related to here, we always want y by itself. So if we tried to get this solved for y, we'd have a slightly different look. Here we go. X, we'd subtract that 1 from both sides. We would then have the y squared by itself. We cannot keep it y squared. We know we need to take the square root of both sides. So if we would take the square root of both sides, we would get y equals, and we should get a plus or minus, the square root of x minus 1. Now, clean or not, that's what we're looking at. Now, that would be the actual equation for the inverse. Okay, we have the original up there. This would be the equation of the inverse that they asked for. Graph the function and its inverse. Now, it's probably going to be easier just to go ahead and graph the function because it was fairly normal looking, and then just do as they say, switch x and y when we go to our graph. So here we go. Back to the original. Y equals x squared plus 1. So we put a 4 in. 4 squared is 16 plus 1 is 17. Put a 2 in. 2 squared is 4 plus 1 is 5. Put a 1 in. 1 squared plus 1 is 2. Put a 0 in. A 0 squared plus 1 is 1. Put a negative 1 in. Negative 1 squared is 1, plus 1 is 2. Negative 2 squared is 4, plus 1 is 5. Negative 4 squared is 16, plus 1 is 17. So we have our original x and y values, and I'll continue to graph the original in pink. So 4, I don't think we're going to be able to hit the 4s here unless we count them by 2s. Let's just do the 2, 1, 0, negative 1, negative 2, and we'll get a fairly good looking graph. All right, so if we go to 2 up to 5, and then we get a 1 up to 2, we've got a 0, 1, point's a little off there, and a negative 1, 2, and negative 2, 5, and obviously we have the 17 up there a little farther for 4. So it's going up quite quickly, and I can't get to 4 until I get out to 17, and I've only got about a 10 right now. So we'd be looking at a parabola-like shape, we know, based on our studies, for this original graph. Now, if we went to blue and graphed our inverse, yeah, you could use your calculator, but you know what? It's probably easier just to take your numbers that you have and flip-flop them like we said. So the ordered pair 2, 5 becomes the ordered pair 5, 2. 1, 2 becomes 2, 1. 1, 0. 2, negative 1. 5, negative 2. And of course we could do the 17, negative 4, that's out there a ways, but again we will draw our parabola style shape, but now it's the inverse, so it's the slanted version, and we would have a really good look at what our original graph looked like and the inverse. And you are going to get some different looking graphs, knowing that we've now opened it up to squareds, cubes, fourth powers, fifth powers. We've got them all in our toolbox. So be ready to see them all. All right? If you have any questions on anything, bring it to class and we'll discuss it.